Hello everyone. This is our first simple example on nodal analysis. I will try to guide you step by step in a specific circuit of how you apply nodal analysis, and I will take you all the way from the circuit to the matrix form. So hopefully this will give you a good idea of what to do and reinforce some of the things that we have already covered in the previous videos. So this is the circuit that we will be dealing with. It has just three different sources. IS1 is a current source, IS2 is also a current source, VS3 is a voltage source, and then it has two resistances, R1 and R2. Now, let me very briefly review the steps and apply them to this particular circuit. Step number one, label all unknown nodes in a circuit. I'm looking at the circuit. I can see that this node here, V1, is clearly an unknown node. I may also label this node V2, and I say I may because if you look slightly more carefully on the circuit, you will probably realize that V2 is actually a known node. And why is V2 a known node? Is because V2 is, of course, the node that connects all the way down here, which means that it's tied down to a voltage source. And in fact, it's tied down to a grounded voltage source, which means that you know that the voltage drops provides a voltage difference of VS3, and you also know that the bottom side of this source is connected to ground, and therefore you have a 0 volts. Essentially what that means is that V2 is a known voltage, which will have a value of VS3 minus 0. Now, plus 0, rather, it really doesn't matter. But I'm going to handle this as if you did not know that V2 is known, and I will handle it as if you thought that you're dealing with a node, with a circuit rather, with two unknown nodes. Very quickly, you'll be able to realize those things yourself, and every time you see a node tied down to a grounded voltage source, you'll be able to immediately recognize that this is a known node. All right, we did step number one. Let's go ahead and do now step number two. So step number two says, go ahead and apply KCL for all nodes, all unknown nodes. Let me focus on V1. It says, all the currents leaving this node must add up to 0. V1 may lose current to the left, and that current obviously will be equal to negative IS1, because there's a current source right there that is pointing to the opposite direction. There might be current flowing downwards through R1, and that means that I will have now to add V1 minus 0 divided by R1. This is the current that flows downwards, and there will be current flowing to the right, and this will be equal to V1 minus V2 divided by R2, and this must add up to 0. So here's my very first nodal equation. I can go ahead and try to put this closer to a matrix form, like I mentioned before. That means I will have to write down that some coefficient that multiplies V1. Let's see what that is. I have 1 over R1 from the second fraction, and I have 1 plus R2 from the third fraction, from the third coefficient, from the third term rather. So I have 1 by R1 plus 1 by R2 times V1. Then I have V2. I have a coefficient that multiplies V2. This is actually negative 1 over R2. So this will be equal to V2. I'm sorry, it will multiply V2. And then I'm done with the unknown voltages, and I have basically the IS1 on the right-hand side as my known current. So here's basically my first equation applied, or rather rewritten, closer to what I need for forming my matrix. So I'm done with node 1. Now I have to go to node 2. Now, if you try to apply KCL the way we have discussed before, you will come up to a slight complication, and so let me show you what that is. I'm looking at node 2. I'm adding all currents that leave this node to 0. Starting first from the left, I will have that V2 minus V1 divided by R2. That's easy. This is the current basically that flows this way. Now I have the current that flows to the south. This is the current right here. So I can write this thing as plus IS2. And now I have the current that goes to the right. Now you look at this current and you suddenly realize, oh my gosh, I have no equation here. Why? Because this is the current that will flow into this voltage source. And unfortunately, we don't know how much current flows to this voltage source, and we have no equation to express that. So you might start thinking, what do I do? My professor never covered that case. No, your professor did cover that case. I told you that when you do have a node that is grounded, that is rather tied to a grounded voltage source, you basically know the voltage. So there is no reason to go through this path here. Node number 2 has the simple nodal equation that says that V2 is equal to VS3. It's the equation I wrote up here. So this is exactly the nodal equation that I need for node 2. So keep that in mind. This is a good example to demonstrate it. Every time you have a node tied to a grounded source, your equation is not this, but rather it's simply this. So now I'm done. I have this equation for node number 1. I already know the equation for node number 2. They're both written very similar to what I need for my matrix form. And if you put them in a matrix, you will get exactly the equation that you see here. So I'm basically done with my problem. I found and I applied nodal analysis for this simple circuit. So once again, I want to encourage you to go ahead and solve this yourself. Write down exactly the equations I wrote down in here, and make sure that your results are essentially the same as what I have given you here. So thank you for watching this video. We will see you next time.